during third lunch, which is why there was such short notice. I thought someone had told me that your test was next week, so I completely misunderstood. Um, I don't have a complete understanding of what's on your test. What I am doing is I pulled some stuff from a review sheet that I got from Coach Emmons, and I pulled some other things, and I'm going to pretty much do this as a teaching. Here's my caveat. I have not taught Algebra 2 in a long time, so I am 99% or I'm about 90% confident with my answers. Not that that should make you feel any better, but if you see me doing something wrong, I could very well be doing it wrong, so please tell us. So that way our life is better. I do have answer keys for most everything because I work through the problems, but just in case, that is what is going on. So here we go. The only thing I just realized is would anyone print it out if I uploaded this to the website? Do you guys want me to upload it as a PDF file to the website? Okay, don't have a printer. Okay. So if you make sure you have pencil and paper to follow along, when we're done, I am going to end up posting these notes. So when we're done, you will at least get to see that, except I just realized that, yeah. So you will get to see them then. So we're looking here. For some reason, my computer has been a little funkety-dunkety the past hour. So hopefully it's not going to impact us very much. Almost all of the work from Algebra 1 got erased, but we do have the video, so that's good. So I'm turning on autosave, so maybe that will make a difference. And also my computer's going slower because I am uploading last session's video. Okay, here we go. So we are looking at polynomials. The main things I learned from Coach that are going to be on your test are things like determining the degree, if there's a root, those types of things. What's the end behavior? So I thought this was interesting. An important and famous German mathematician, Carl Friedrich Gauss, is credited with proving the fundamental theorem of algebra, which states every polynomial equation of degree 1 or greater has at least one root in the set of complex numbers. We can use an extension of this theorem to suggest that a polynomial of n degree must have n linear things. So what does that mean? Well, all that means is look at the degree, and whatever that degree is, that's how many roots you can expect. Not necessarily imaginary versus real or rational, but just how many roots. So when it says degree is when it's in standard form, is just whatever the exponent is. So your degree is your exponent. So in this case, how we had x is 4, our highest exponent is 4. So we could expect to have 4 factors. Here, even though this isn't in the right order, here our exponent is 3. Here our exponent is 5. Here our exponent is 6. Here our exponent is 1. And here our exponent would be 0. So the highest number that we have is 6. So that's how many factors that we would have to have. Does anyone need me to clarify how to find factors? Or how to find how many factors? The only thing that's a little bit trickier is if you get to equations that look like this. And let's look at it right now. Here in number 1, it's not as simple as number 2. In number 2, there's no multiplication going on. Each one of these monomials is its distinct idea. So our highest factor, or I'm sorry, our highest exponent is 3. So that means that there's going to be 3 roots. Here, everything is getting multiplied together. So we don't just look at, oh, 2 is the highest root. That's not how we do this problem. Because everything is being multiplied together, we have to add the roots. So write that down. When polynomial parts are being multiplied, then add the exponents. So in this case, this x has an exponent of 1. The x plus 3 has an exponent of 2. And my x minus 5 has an exponent of 1. So then, because all my polynomial parts are being multiplied together, all I'm going to do is add the exponents. So in this case, I've got 1 from the x, 2 from the x plus 3, 1 from the x minus 5. So 4 is the number of roots that I could get. So very similar to the other one, except because all of them are being multiplied together, we have to make sure that we add the exponents. Moving on. Now we're going to analyze the graphs. And when we analyze the graphs, we're trying to determine, okay, what are the roots and what's happening at the roots? And when we say roots, all we're saying is what happens when the graph crosses the x-axis. That's all roots are. Roots are when our graph crosses the x-axis. That's it. So we really want to know what's happening. So first of all, this says lists all the roots, list all the zeros of f of x. So roots and zeros are synonyms. So if I look here, I can see that something happens at -2, something happens at -1, something happens at +1, and something happens at +3. Those 4 are what my zeros are, or those are the roots of my equation. Now it says, assuming all of the factors of the polynomial are real, and the leading coefficient, all that is the number that's first, is 1, what could the function be? Well, because nothing special happens, there's not something that's called a multiplier. We know that 4 times it crosses. Well, if it crosses at -1, we have to do the opposite. So it tells us our leading coefficient is 1. So I'm going to put a 1 here. Then I'm going to do, okay, well, if I have x equals -2, what do I need to do to make it 0? Well, I add 2 to both sides. So really, I know that x plus 2 equals 0, so that's what I'm going to write here, x plus 2. Then I've got x equals -1. So what do? I add 1 to both sides. So I get x plus 1 equals 0. So that's my next one. Then I've got +1. So I know I'm going to do the opposite. So that's going to leave me with -1. And I've got x is equal to 3. So I'm going to be left with x minus 3. All of these are getting multiplied together. Then it says rewrite it into expanded form, which is just crazy. So first of all, I'm going to see what is easy. Well, one thing that I noticed that is easy is here I have a +1 and a -1. So you should have learned that that's difference of 2 squares. So if I do x plus 1 times x minus 1, that's just going to get me x squared minus 1 because the insides cancel. So right here, I'm going to write x squared minus 1. Then I'm going to multiply x plus 2 times x minus 3. And then we have to multiply all that together. It's literally so much of algebra. That's probably why it's called algebra 2. So x times x is x squared. X times -3 is -3x. 2 times x is 2x. 2 times -3 is -6. Combine like terms. Now we put that all the way over here. And then we distribute one more time. It's literally that annoying. I'm sorry, coach. It's just annoying. So we've got x squared times x. Wait, what am I missing wrong? Oh, no, I'm fine. So I've got x squared times x squared, which is x to the 4th. Then I've got x squared times -x, which is -x cubed. Then I've got x squared times -6, which is -6x squared. Now I do the inside. -1 times -x squared is -1x squared. -1 times -x is +x. -1 times -6 is +6. And then, and notice how I just lined up the x squared. So that's just going to allow me to add going down. So I'm left with x to the 4th minus x cubed minus 7x squared plus x plus 6. And that's it. So we see, well, what's the degree? 4. How many zeros are there? 4. So we know that we most likely did it correctly. All right, let's take a look at another one. Here it says, consider the polynomial function g of x that has those zeros. Okay, what is the minimum number of degree this function can be? Well, here's something I learned. It doesn't necessarily, oh, never mind, that's behavior. So first we're going to count. Well, here's 1. Here's 2. Here's 3. So what's the minimum possible degree? 3, because I have 3 roots. However many roots you have is going to help dictate what everything else is going to be. Now it says, assuming all of the coefficients of the polynomial are real, and the leading coefficient is 2, what's the factored form? Well, because it tells me that leading coefficient is 2, that's this part, 2. Then everything else is just doing the opposite. The opposite of x equals or +3 is subtract 3. The opposite of this one, which is minus the square root of 2, is plus the square root of 2. The opposite of this one, which is plus the square root of 2, is minus the square root of 2. And then that's it. Then we look for what's easy. Well, I would think what's easy is doing these. So we're going to, that's difference of 2 squares again. So really that's just going to give me x squared minus 2, because these will end up canceling, and the square root of 2 times the square root of 2 is +2. And then here, when we distribute, we get 2x minus 6. And then we have to do it all over again. Yay! Don't we just love multiplying polynomials and binomials? 2x, or x squared times 2x is 2x to the 3rd. X squared minus 6 times -6 is -6x squared. Here, that's going to be -4x. And then here is going to be +12. And that is our answer. Okay, so again, it's just taking it step by step, going through, and then what do you see in common? Doing the opposites. Once you have the opposites, if you need to put it into expanded form, doing the polynomial multiplication. Okay, next, number 7. Now we're going to interpret this, and we're going to talk about something called multiplicity. And Mr. Smith taught me about multiplicity. Now, anytime we have an intersection, that becomes our multiplier. So let's look at this following function. Here, it takes a pit stop, so it's literally like we drive right through the -1. Here's +1. We drive right through the +1. Look what happens when we get to 3. When we get to 3, we go down, but it's not like we just like keep going through and go straight. No. Instead, it's like we stay a while, we drink a milkshake, and then we go back. Anytime you have a parabola, that is going to be a quadratic, and that is going to be a multiplier of 2. So here we have our -1 as one of our roots. We have +1 as one of our roots, but really this 3 is used twice. It's called a multiplicity of 2. And what that means is we use it twice. We use it once going down and once going up, because we have a turning point. It gets to be used twice. So assuming all the values. Well, we already know it tells us the leading coefficient is 1, so I'm going to put 1. Then let's just go in line. Here we have x minus 1. So what do? We multiply by the opposite, which is x plus 1. Next, we have positive 1 here, so we're going to multiply by negative 1. But then we have that interesting multiplier. And because we have that multiplier, what that means is we're going to write our x minus 3, but we have to write it twice. We have to write it once going down and then once going back up again. And that is really how we get our quadratic, is we get it once going down and once going up. Then it wants us to do the math again. Well, here we have difference of 2 squares. So that's just going to be x squared minus 1. Here, you should know anytime you do a squared, you just add. So negative 3 plus negative 3 is negative 6. And then we do our long multiplication again. X squared times x squared is x to the 4th. X squared times negative 6x is negative 6x cubed. X squared times positive 9 is positive 9x squared. Now we do our insides. Negative 1 times x squared is negative 1x squared. Notice how I'm lining the x squareds up. Negative 1 times negative 6 is positive 6x. Negative 1 times positive 9 is negative 9. And now, because I lined up all my like terms, I can just add going down. X to the 4th minus 6x cubed plus 8x squared, because 9 minus 1 is 8, plus 6x minus 9. And again, we can see the degree is 4. It doesn't look like 4, but it is, because we have 1 here, 2 here, 3 as we're on our way to get our ice or our shake, and 4 on our way going home. So that's why it has a degree of 4. All right, let's look at this again. Based on the degrees of the polynomial function and the graph, determine how many real and how many imaginary zeros the polynomial must have. Here you go. I have no exact remembering of how to do the imaginary zeros. I'm sorry, but we'll still figure it out. Okay, so if you know, feel free to chime in. Okay, let's look at the graph. First of all, we're going to see how many times or how many zeros that it has. Well, this right here tells us it's a 3, so we know that we're going to get 3 numbers. What are our 3 roots? Well, let's see how many times it crosses. 1, 2, 3. So that makes sense. So what are the number of zeros is 3. So we're going to have, what are they at? We know, well, one of them is at -1. One of them is at +2. One of them is at +3. So if I had to write my equation, all I do is switch the signs. -1 becomes +1. -2 or +2 becomes -2. +3 becomes -3. All right, next. Yes. -3, 2, 3. Okay, yep, got it, Math Whiz. You're right. All right, moving on. Owens, if you can help me with imaginary zeros, I don't know how to do that, but I don't think it's going to be on their test because I pulled this from a different resource. Okay, looking here, same idea. We know that there's going to be 4 roots because of that. Okay, this one is not going to be on your test because I saw your test. All right, let's look here. This has a degree of 5, but again, yeah, Owens, I don't know. They should not have pulled this because again, this is imaginary and imaginary zeros was not on your test. So the only one that we really need to know was the first one. All right, moving on. Factoring is going to be on your test. There's different things to factor. I found this slide and I really liked it because it kind of shows you how to look for what they have in common. So if we go here, we notice that this has a y, this has a y, and this has a y. Because the y is common in all of them, we can pull it out. So all I'm going to do is I'm going to take that y and throw it on the outside. When I throw it on the outside, I kind of cancel it because I'm doing reverse distribution. I'm doing factoring. So then I look at what's next. Well, 7x is left, plus 10 is left, and minus 5z is left. That's all factoring really is. It's looking for what do they have in common and what can I pull out because of what they have in common. Next, here it's also kind of color coded. we notice that all of these have 2x minus 1 in common. So because all of them have 2x minus 1 in common, I can pull that 2x minus 1 on the outside. That's going to leave me with 3x plus 4 plus 2x. But here's what's really interesting. Do you see how inside those parentheses I have like terms again? I have a 3x here and a 2x here. So now that I've pulled that out and I have all of those ideas in one set of parentheses, I can group them. So I still have my 2x minus 1 on the outside chilling, but inside I can do 3x plus 2x for the 5x and then the plus 4. And then I factored that. Okay, let's look at another one. Here, again, highlighted for us, the a plus 3 is consistent. A plus 3, a plus 3. So now I can pull this out. I have my a plus 3 on the outside, and then on the inside, I have a squared minus 9. But you should have learned something about a squared minus 9. A squared minus 9 is that difference of two squares. So we know that we can take a squared, and if we take the square root of it, we're left with a. When we have 9, we can take the square root of 9 and be left with positive and negative 3. So this a plus 3 for right now stays on the outside. This a squared plus or minus 9 now becomes a plus 3 and a minus 3. Here we go again. Look at what they have in common. All of this is being multiplied together, but we have two binomials that are a plus 3. So because of that, all I need to do is make it look great and make it look nice and sharp and put it as a squared. So my answer is going to be a plus 3. I'm going to square it like a multiplier because there's two of them, and then a minus 3 on the outside. All right, next. Same type of idea here. We have the 3b minus 1, and you have the 3b minus 1. So I can pull out 3b minus 1 all by itself. What's left is 2a plus 7 plus the 3a minus 2. Then I can notice, well, look what they have in common. They have the a's in common, and they also have the constants. Both of them have constants that we can combine like terms. So when I do this problem, I'm still left with my 3b minus 1, but now I can simplify it. I can combine those like terms. 2a plus 3a leaves me with 5a. 7 minus 2 leaves me with 5. And that is that solution. Okay. A couple other ones. Let's talk about factoring by grouping. So that's similar factoring, but here you have to discover kind of what they have in common. One of the first things to look for is exponents. That's going to be your key thing to look for when it comes to factoring by grouping. So when I look at my exponents, I notice here's x cubed and here's x squared. So that's good because they both have at least x squared. Then I can also see, well, look, this has a 5 and that has a 20. So I can also look at the coefficients or the numbers. So what I'm going to do first is I notice if I look at the purple, one has an x cubed and one has an x squared. So I'm going to pull out the x squared. And when I say pull out, all that means is I'm dividing each one of these things by x squared. That's all I'm doing. Then what I'm going to do is I'm going to say, okay, well, what's left? Well, if I have an exponent of 3 and I divide it by an exponent of 2, these cancel and I'm left with an exponent of 1. If I do that here, these cancel and I'm left with just plain 4. So that's my first part. Then I need to factor my next part. And I notice that both of them have 5 in common. So I'm going to put plus 5 on the outside. Well, if I divide each of these terms by 5, I'm left with x, because 5 divided by 5 is 1, so I'm left with x. And then 20 divided by 5 is negative 4. And then look what I did. That's exactly what I wanted. See how this says x minus 4 and x minus 4? It means I did my grouping correctly. That's when you start to celebrate. Now that we're celebrating, we just do our final step. And our final step is to pull the outsides together and leave that inside that's the same right here. And that is our final answer. So all we did is similar to up here where we looked for what do they have in common. See how they had the a plus 3 and the a plus 3. That's what we did here. We did one step first to kind of separate it out, but then we noticed, oh, they both have x minus 4. I can pull that down and I can pull out the leading coefficients, the x squared and the positive 5. All right, let's take a look at this one again. All right, here we've got m cubed and here we've got m squared, so they could group. And here we've got a 9 and a 12. They have something in common there. So then let's do that same process again. Well, if we take out here, we also can see we've got a 6 and an 8. So let's pull out 2. Let's just hope this is a perfect problem. So we're going to pull out 2m squared. Now remember, when we do that, all we're doing is dividing both of these by 2m squared. So when I divide this by 2m squared, I have 6 divided by 2, which leaves me with 3. And then this becomes just plain m. Here, again, I'm going to divide by 2m squared. Well, easily enough, the m squareds cancel. So I'm just left with 8 divided by 2, which is positive 4. Now I got to look at my next set. Well, my next set, I have a 9m and a 12. Well, I know that 9 and 12 have 3 in common. So if I divide 9m by 3, I'm going to be left with 3m. And if I divide 12 by 3, I'm going to be left with 4. And look, we did it right again. Yay us. Here's the 3m plus 4. Here's the 3m plus 4. So because they both have 3m plus 4 in common, I can pull that out and then take the leading coefficients and turn it into its own binomial. So that's what I'm going to do. I'm going to take this 2m squared plus this 3, and that's going to be its own binomial. Then I'm going to take this 3m plus 4 and this 3m plus 4 and just put it by itself. Okay, does anyone need me to do another problem, or do we know this enough? Okay. Yes, no, you can just type. You can put your mic on. Do we need to do another one of these, or are we good? Oh, I have a problem on my review. It says to factor 5p cubed. I think I have that one on here. Yep, I do have that one. Yep, so let's do this. All right, so if you have it on your review, we'll look at questions 3 and 4 and 5. Let me switch to my review notes. Okay, so again, for this one, for number 3, again, we're looking for what do they have in common. So what we're going to do is we're going to highlight, here's our p cubed, here's our p squared. We always look, are there exponents that are big? Then if we can find exponents that are big, we're going to look for coefficients in the next set. So I've got negative 25 and negative 30. So first, let's talk about the 5p and the 5p cubed and p squared. We know that they both have p squared in common because there's no number that's in common between the 5 and the 6. So I'm going to divide both of these by p squared. These cancel. This becomes just 1. So inside I'm left with 5p plus 6. Now I'm going to look at my next section. I'm going to say, well, between negative 25 and negative 30, I know that negative 5 can go into both of them. So I'm going to divide both of these by negative 5. Because I'm dividing both by negative 5, I'm going to pull the negative 5 out. Negative 25 divided by negative 5 is positive 5, and the p just comes down. Negative 30 divided by negative 5 is positive 6. Then I notice, holy moly, look what happened. Here's 5p plus 6. Here's 5p plus 6. We must have done it correctly. So then I just say, okay, what do they have in common? We have p squared minus 5 here. And we have 5p plus 6 here. And then it's done. So we'll go through all of these, but that is pretty much what we're looking at how to do it. Sweetie, turn off your camera. Everybody can see you. Okay, next. All right, let's look at this next one. This next one is just basic factoring. I did a whole video on factoring before. Let's look at it again. Some of you learned something called the X method, where you put negative 42 here and 1 here or something. I don't know the X method. I don't do it that way. This is how I do it. I know that I'm going to have two binomials. Because this says X, I'm going to put X here and X here. Because this is a negative, I know I'm going to have to multiply a positive times a negative, because that's the only way I can get a negative number is by multiplying by a positive times a negative for my C term. So then I think, okay, what are the possible ways I can get 42? So I could get 1 in 42, but that's either going to give me 40, that's going to give me 41 or negative 40, or 41. So that's not going to be good. I can do 42 divided by 2 to get 21. Well, that's only going to be a difference of 19, so that's not going to help. I could do 3 and 14. Well, 3 and 14 is a difference of 11, so that's not going to help. 4 can't go into it, 5 can't go into it, 6 can go into it. Oh, 6 and 7. Can I get 1 out of that? Yep, 7 minus 6 is 1. Now, because this term right here is positive, I know that the positive has to go with my larger number. So this has to be a 7 and this has to be a 6. And now that is factored. I know your teachers taught you other ways. There's another way that you can do something, I guess, like this. But I don't know it well enough to teach it. So that's another way that you can do it. All right, here I was told the easiest way to do this problem is to just solve it because you have two terms. And so what I mean by just solve it is subtract 64 from both sides, because we're going to isolate our variable. So we have 9x squared equals negative 64. Then we divide both sides by 9 because, again, we're trying to isolate the variable, which means we have to remove the leading coefficient by doing the inverse operation. That's going to leave me with x squared equals negative 64 over 9. Now, when I take the square root, I really take the square root of the numerator and I take the square root of the denominator. So that's going to leave me with x squared equals, well, remember, anytime you take the square root of a negative number, you got to put an I. So the square root of 64 is 8. The square root of 9 is 3. So your answer is, x equals plus or minus the square root of, x equals plus or minus 8/3 I. So let's look at another one real quick. So here, if I had this problem, again, I would subtract 25 from both sides. Don't ask where I got it. I just made it up out of my head. That leaves me 16x squared equals negative 25. Divide both sides by 16. That leaves me x squared equals negative 25 over 16. Well, because I am taking the square root of a negative number, I know that whatever I get, I has to be on the outside. Well, the square root of 25 is 5. The square root of 16 is 4. And again, because I'm doing square root, I have to put in my plus or minus. Okay, this next one says solve for p using your preferred method. First things that you have to do is you have to get it set equal to 0. So I'm going to add 8 to both sides. That's going to leave me with p squared plus 16p plus 89 equals 0. Here's what sucks. 89 is a prime number, so I can't factor it. I have to use the favorite quadratic formula, which if you participated last time, I'm pretty much sure I sang to you. So the quadratic formula, I remembered it, and to the tune Row Row Your Boat is, it's on your formula sheet, but it's x equals the opposite of b plus or minus radical b squared minus 4ac all over 2a. I'm not going to do all of it for you, but we know that a is going to equal 1, b is going to equal 16, and c is going to equal 89. Then all you do is you plug in those values into that quadratic formula, and you're going to get your answer. It's as easy as that. Here, I'm going to put in the opposite of b, which is negative 16, plus or minus b squared, so 16 squared, minus 4 times 1 times c. All I'm doing is substitution. And that is all over 2 times your a value. And then you solve. Okay, let's go back to the other things I pulled. All right, let's take a look here. Here in this problem, again, we're going to do more practice with this with the review sheet you got from your teachers. But I just want to kind of teach it to you first so you have it. And then I might need to pull up a couple other things because I don't think I copied everything over. Come on, paper, where are you? Number 9. Okay, now it says, I didn't put the directions, but the directions say factor the following polynomial functions, analyzing the graph of the function to help you. So let's take a look. Well, here we have this point, which is at negative 1. These are our roots, positive 1, and positive 2. So all we need to do once we have that is just write the reverses again. So here we're going to have technically f of x is going to equal x, the opposite of negative 1 is positive 1. 1, that's going to be negative 1. 2, that's going to be negative 2. And there you go. Let's look at the next one. Here we have it at 0, and it just goes through. Notice all of these, it just goes through. It doesn't turn and change direction. Here at 2, though, look at what happens. It goes down, we get our milkshake, and then it goes up again. So that means it's a multiplier. Remember, anytime, or multiplicity. Anytime that you have a swoop, I don't know what, I heard that you all call things like whoosh and everything else. Forget it. Anytime you have a parabola piece, that's when you're going to have your multiplicity part. So we know our zeros are at 0 and at x equals 2, but this is a multiplicity, so we really have x equals 2 twice. Once going down, once going back up again. So when I write it out, I know I got to do my opposite. I got x first, then I have x minus 2. Every time the x, okay, if the x bounces like this, yes. If it goes up and then levels out, no. It has to do a bounce. It has to start. It's like I went to Kroger to get tiramisu and then I left Kroger. I went to school to get my lunch bag and then I left school. So anytime it makes a quadratic or looks like a little parabola, yes, it's going to be a multiplicity. And then here we have our x minus 2 again. Yes, it has to bounce on the x-axis because you're looking at roots, and our roots are connected to the x-axis. Okay, so that's why it didn't have multiplicity on number 9, because on number 9, it didn't turn at the x-axis, but it did turn at the x-axis because there was a 0 at there. So this is our multiplicity is 2, and it's because we had a 0 at x equals 2. Good questions. All right, let's go on. Here it crosses here at about negative 2.5. Here it crosses at positive 1. Here it crosses at positive 2.5. So it's the same kind of idea. Hold on one second. Okay, this one is one that deals with the radical, so we're going to skip it because I don't want to deal with radicals here. Let me look at the next one, and the next one also has a radical. To my knowledge, on the test that I saw this morning, or earlier today, you will not have anything that relates to radicals, so that's why we're going to skip it tonight. Let's just try to touch what you're going to see tomorrow. Okay, next one. This is kind of going to be interesting for me. It says identify the leading coefficient as either positive or negative, and identify the degree as either even or odd. Okay, so here, if it has the same end behavior, then our degree is going to be even. If it has opposite end behaviors, I don't know why I wrote bend. Oh, that's why. Then our degree is going to be odd. And when it says end behavior, this over here is the real end behavior, but we're also looking at both. So here we have it pointing to the positive. Here it points to the negative. So this is an odd degree. We don't know how many. We don't know if it's a degree 5, a degree 7. We don't know. All we know is that it's odd. Same thing here. This one starts down. It ends up. So it's opposite. So because it's opposite, we know it's going to be odd. Now we look at what the leading coefficient is. And I wrote first down, so it's negative. First up, it's positive. Okay, so my leading coefficient, when I look at this, is what's happening? Well, first, it's going in a downward direction. So my leading coefficient is going to be negative. Because it's going down. Here, when I start at my end behavior, what's happening to the graph? It's going up. So my leading coefficient is going to be positive. And to be transparent, I just learned this part today. So if you learned something else, chime in, but this is what Mr. Smith and I came up with earlier. Okay, now we're going to take this a little bit harder. Even though it didn't ask us, we're going to try to write it one more time because it's a little bit more complex. So it's not going to be completely perfect. It's probably got radicals in it, but for our purposes, let's pretend there's no radicals and it's just going to be like 2.5. Okay, see here how it went down to get an ice cream and then it went up. That is at -5. And because it goes down and up, this is going to be our multiplicity. Okay, then it crosses right here at -1 and it just goes straight through it. So it only happens one time. Now this is where it gets a little interesting. See how it kind of is flat? Anytime you have flat, that means it's going to have a degree of 3. So real quick, if it crosses the axis, that's going to be a degree of 1. If it just is a straight cross. If it touches the axis and then turns around immediately, that's when we have our multiplicity. And this is not, I was told, always the case, but for Algebra 2 purposes, it is the case. It's a multiplicity of 2. And if it goes up or down and then stays a while and then continues on its journey. So here how it stays, it's going to have an odd degree, but for our purposes, we're going to say it's a degree of 5. I'm sorry, sugar shoots, a degree of 3. So this is what I just learned today. So hopefully this is aligned to what you have. So when I write this, I notice at 5, it makes my little yoop. Okay, I got ice cream quickly and then I left. So I know that for -5, I'm going to end up needing to have a square. Here at -1, it passes right through, so it's going to have a degree of 1. Here my degree is 2. That says degree, not dog. Here at point 4, we stay a while. And when we stay a while, for our purposes, it's going to be degree 3. Now, I have learned it's not always a degree 3, but for our purposes, it's a degree 3. And then finally at 7, it just goes swoosh right down. So that is going to be a degree of 1. So now that we have the information, we can look at what's our highest degree and work backwards. Our highest degree happened right here, a degree of 3 when our root was 4. So how do we get to have a root of 4? Well, we do the opposite. So I'm going to write down x minus 4 with a degree of 3. If you get confused, we're going to do it again for the next one. Then here I've got, okay, what's my next one? My next degree lower is a degree of 2. So for my degree of 2, right here, I've got negative 5, but I have to do the opposite. So I'm going to put x plus 5 with a degree of 2. Now I look at, okay, what's my next exponent? I've got 2 of them. I've got a negative 1 and I've got a 7. So both of them, it doesn't matter what you put first, so I am told. So I'm going to write down my x, switch the sign, positive 1, x, switch the sign, negative 7, and then this would be the equation of that long, crazy thing. Okay, so let me copy this slide, and then we'll do it again for the other one. Let's see. Okay, so let's look here and we're going to do the same type of thing. Okay, remember, if it just goes through, if it just is passing through and just crosses over, it's a degree of 1. For our purposes, if it swoops and just turns around and goes in the same direction, that's going to be a degree of 2. And if it climbs and stays a while and then keeps going, for our purposes, it's a degree of 3. Is it going to be like that in real life when you get to pre-calc? Nope. But for Algebra 2, that's what we're telling you. Okay, let's take a look here. For our purposes, we're just going to have this be negative 1. It crosses again right here. Let's say negative 0.25. I'm just estimating. Here it crosses at, let's say, positive 1.25. Here, let's say it crosses at 1.75. And then here it crosses exactly at 3. Go figure. Okay, so our numbers, none of these, every single one of these, it just crosses. None of them turns exactly at the 0. None of them stays a while. So all I'm going to do is write the opposites. Opposite of negative 1, positive 1. Opposite of negative 0.25, positive 0.25. Opposite of positive 1.25, negative 1.25. Opposite of positive 1.75, negative 1.75. And then opposite of positive 3 is negative 3. So just breaking it down step by step. All right, let's look at another one. Same type of idea. Number 9. Which is right here. Okay, for number 9, let's first find our main zeros. We have something happening at negative 2. At negative 2, it goes straight through it, so we know negative 2 is going to have a degree of 1. Then it crosses the x-axis again at 0, but look what happens. It goes up, it stays a while, and then it continues on. I learned it as that it was called a terrace point. And I kind of like it. If you think about a terrace, it's like an outdoor porch. So it's just like you're chilling on your outdoor porch, drinking some lemonade. Then it crosses again at 2. What does it do? It just goes straight through it, nothing else. So that's going to be a degree of 1. Then I write my opposites out. Now that I know my roots, I can write my opposites. Here, opposite of negative 2 is positive 2. Here, my degree of 0 is just going to be x third. Here I've got my degree of 1. With 2s, the opposite of positive 2 is negative 2. And then you can just rewrite it to make it look pretty. And what I'm betting that they probably want you to do, did I do it like this? Yep. That's how you can do it. If you want, you can make it look even better and notice that, oh, this is a difference of 2 squares. So really, this is x cubed times x squared minus 4. And then you can take it even further if they want it to be all the way together. X cubed times x squared is x to the 5th. X cubed times negative 4 is negative 4x cubed. And that is your answer. All right, number 10, sketch the graphs. Okay, here, let's see what's going on. We've got negative 5 because we do the opposite. Here we have x equals negative 1 and x equals positive 4. Technically speaking, we're not doing the opposite. Technically, what we're doing is we're putting x plus 5 equals 0, subtracting 5 from both sides, and getting x equals negative 5. Quick way is just do the opposite. All right, so my important points are negative 5, positive 1, and positive 4. Now, there's no kind of duplicity, anything going on. And then what I look at is I say, okay, what's the degree? Well, here I have 1 as my exponent. Here I have 1 as my exponent. Here I have 1 as my exponent. So when I add 1 plus 1 plus 1, my degree is 3. So now I know that my degree is 3, so I'm going to have 1 that goes up, 1 that goes down. All right. Also, I know that it's positive with the start going up because I don't have any negatives in the front. Like there's no negative here. If there was a negative here, it would be different. So all I'm going to do to start my sketch is, well, I have to go up to 5. Then you really don't know what happens. So, oh, what did I mess up on? Ooh, this should be negative 1. Oops, my bad. This is why you do the answer key beforehand. Then I swoosh, pass right through it. Then I got to go back up through 4, and then I go on. Now, I don't know what the slopes would be at any interval like that. All that I do know is I know that my domain and my range is going to be negative infinity to positive infinity. That's my main part because I can go all the way down this way, all the way up this way. Here's a hint. If on your test it asks you what the domain and range are, 99% of the time for your test coming up, it's going to be negative infinity and positive infinity. Just saying. Pay attention to the arrows. That's that one. All right, let's look at another one. Here we've got our negative x squared, and here is our multiplicity. That's what we see. Okay, we know it's multiplicity because of this 2. So first, we know that we have a 2 here and a 1 here, so our degree is 3. Because our degree is 3, we know that our end behaviors are going to be opposites. Because this is negative, my graph is going to start by going down, and we know my critical points are at negative 3 and positive 3. So I'm going to start by going down, hitting my negative 3. But see how this is squared? That's my multiplicity. So it's not just going down, it is going down and looping back up at that point. Then my next point is 3. At plane 3, it's linear, so we just loop down and cut right through it and go on. Guess what my domain and range are? Yep, negative infinity and positive infinity. All right, that is all I was going to show you. The only other thing on here, I know there's other types of things, but when I was talking with and took a peek at your test, I was just going to stick with these. Unless there's a question you definitely want me to go over, you can let me know and I can pull it up. But that is the foundations. I didn't want to overwhelm you because I know a lot of you guys are already struggling with it. So that was the goal to end tonight. because it's already 9 o'clock and we all have to get up early in the morning. Okay, so I guess if that's it, if you guys want to put your names in it, I can give it to your teacher. Otherwise, I'll just copy this and I will see you guys tomorrow at school. So have a good night. Thank you so much for joining. Bye.